Next we look into another problem that occurs when we are connecting outputs of 2 or more logic gates together or say logic blocks together. So, this comes under the broad heading called open collector or open drain gain. Now, this if you remember this term drain we have seen when we talked about this CMOS transistors, and this collector. So, collector term we have not seen. So, this is basically coming from the fact that previously if you look into in the logic family. So, there was a family called TTL, transistor logic, and in the transistor logic. So, the circuits were realized by means of transistors. So, a transistor has got 3 terminals, one is known as the base terminal. So, this is the symbol of a transistor. This is the symbol of a transistor. So, this terminal is called the base terminal, this is called the collector terminal, and this is called the emitter terminal. Okay. So, architecture wise, so it is like this. So, we have got this if you say that okay, we have got a silicon wafer, then some part of it is the emitter. Then after that we have got a thin base. So, this region is called base, and then this is called the collector. Now, this particular transistor that I have drawn here, this emitter is of N type, base is of P type, and this collector is of N type. So, this is an NPN transistor it is called. Okay. So, electrons they go from emitter cross this base and reach the collector region. So, that way the current flow is done. Anyway, so that is a different issue. So, this logic gates can be realized using this type of transistors also, because that also acts as switch. Now, the current that can be drawn, like say if I have got some circuitry here. So, if I have got some circuitry here which is say TTL circuitry, and then it is connected to the supply voltage which is in general known as VCC. Okay. So, this is the output of the this is the some logic is realized here, and this is the output of that logic, and it is feeding some load here. Load is generally shown as a capacitive load, because the charging current is necessary for taking the particular signal point to logic high. So, the amount of current that can be drawn here is limited. Okay. So, it is limited by the TTL family, TTL logic family. So, it is not very high. Now, so if you have to connect large number of inputs from this output, so it creates problem. So, another difficulty that we have with this TTL family of logic is that, suppose here we have got 2 blocks A and B, we have got 2 blocks A and B, and then so these outputs of A and B, so they are shorted together. Now, if A equal to B, then output is, so there is no conflict. So, A and B are same. So, output also is equal to that value. However, if A is not equal to B, so what can happen is that say A equal to A output is 1 and this output is 0. So, that means A is trying to pump in current like this and B is trying to sink current like this. So, as a result there may be a large amount of current flow through this circuit. Okay. So, a large enough current that can get created, and this current may be so high that these transistors that are there in the lower part of this B logic block. So, that may not be able to withstand that current. So, it may damage the circuit. So, a large enough current can be created that causes excessive heating and could damage the circuit. So, what is the way out? Okay. So, this open collector is a solution to this problem, and so this is also there are on the CMOS family, if you look into, so they are called open drain connection. So, open drain, so you know that in CMOS it is in CMOS there are 3 terminals like this, one is called drain, another is called source, and another is called gate. Okay. So, here also with the, so if this drain is connected, normally it is connected to VDD side, and this is ultimately connected to the ground, and this G is getting the input. So, in the process, so it may so happen that in some of the logic families, so this drain is not connected to the supply voltage, because of the same reason that if you have to drive a large load, it may create some problem. So, we will see how this can be solved, like say here. So, one possibility is that we can use some sort of multiplexer. So, multiplexed output lines using 3 state buffers. So, this solution we have seen some time back, so like this A and B. So, these are the 2 block outputs, and we put some tri-state buffer here. This is controlled by EN A and this is controlled by EN B, and this S, this actually for multiplexer it is selected, since the multiplexer. So, it will select one of these 2 outputs and that will go to the outline. So, if S equal to 0, then this input is equal to 1 and this enable B is equal to 0. So, this being equal to if S is equal to 0, so this is equal to 1. So, as a result this A output is passed through this buffer to the output. Similarly, if S equal to 1, then this enable B is equal to 1 and enable A equal to 0. As a result, this output of B, it passes through this buffer and it comes to the output. So, if you look into the truth table, you see that for this combination, when enable A equal to 1, and naturally in that case enable B has to be 0. So, whatever be the value of A, that comes to the output, and similarly when enable A is equal to 0 and enable B has to be 1 in that case, then whatever be the value of B, that comes to the output. So, this way we can realize this, we can use these 3 state buffers or tri state buffers for this type of multiplexed realization. But you see that this does not always solve the problem, because many times we do not want this type of multiplexing. We just want some logic by which that will be followed when this type of sorting of 2 lines are there. So, they come under this under the broad heading called open collector or open drain gates. So, outputs of some gates may be wired like this. So, if it is A and B, so they are connected like this. Now, this so this what is the logic that you get at this point? So, that is the functionality that you get is dependent on the logic family that you are using. For example, if you are using TTL technology, then this connection, so this will result into AND operation. So, O1 and O2. So, you will get the AND operation. Similarly, for open drain gates in CMOS technology, so that you will get an AND operation. Okay. So, you will get a output as the AND of these 2. Now, can I connect this 1 and O2 like this? So, logic level is fine. So, logic level, logic value I get as AND of this and all things like that. So, if I do not use open collector, if I use normal TTL gate or normal CMOS gate, then also I will get the output as O1 O2, but the problem that will come is the current flow through the lower device, the current flow through the devices that can occur if one output is high and another output is low. So, for that purpose we need some protection. So, what we do, we put a tri-state gate here. So, this is this is known as the wired AND. So, this AND gate is physically not there. So, it is just the 2 wires that are connected, that are shorted at this point, but it essentially gives the AND operation. Okay. So, this gate is the wired AND gate we say, okay, and but physically there is no such AND gate. So, open collector or open drain NAND truth table is like this. So, if you this is open drain. So, if this AB is 1 1, then only output is 0. So, since the problem with this open collector or open drain is that you see if this is your open drain gate, this is the open drain gate. So, this is my drain. So, this is gate, this is source, and whatever be the connection. So, in this lower part of the logic, suppose this gate is equal to 1 and that we are taking the output from this point, okay, sorry, not from this point, we are taking the output from this point. Now, if this transistor is say off, if this transistor is say on, then this side is eventually connected to ground. So, this will be going down to 0. So, if this NAND gate both the inputs are 1, then this then there is a current flow path, like in the NAND operation this lower end network is shown like this. So, this is A and B. So, we have got so this is grounded and suppose this is open drain. So, I am connecting it. So, this side is open, it is not connected to VDD. Now, what will happen is that if I put a 1 here, so these two transistors will be on. So, this is also on and this is also on. As a result, this value voltage will become, this point voltage value will become equal to 0. So, for 1 I am getting a 0, but if any of them is equal to 0, sorry, if any of them is equal to 0, then I do not know what is the value here, because that side, so this lower side is cut off and upper side is also not connected to any voltage source. So, this is open, fine. So, this is as if so it is high impedance or high Z, as if it is unconnected. So, this if these switches, so these switches are connected, if both the switches are equal to 1, then this switch will drop down as if I will get a connection to 0. So, this way it operates. So, what to do if I do not have this if I do not have any connection to the supply voltage. So, what it says is that you need a resistor to pull it up when one of the input is equal to 0. Let us see how this is done. So, this is the situation. So, we have got this point. So, we have got this if this A and B both of them are 1, then definitely this F point is getting connected to 0 and it is getting 0 here. So, but if both of them are equal to 1, if both of them are equal to 0, in that case what I will do, I will be pulling this to this F point to high via this resistor. Okay. Similarly, so if A, B, C, D all of them are equal to 0. Okay. If all of them are equal to 0, then so all these switches are open. So, in that case, at this addition of this extra resistor here, so that will ensure that at this point you get a 5 volt value. So, this is outside the chip. So, this resistor and this supply, so this is outside the chip. So, from inside the chip I am getting just these switches as open. So, this point, this line is open, similarly this line is open, and by means of this external resistor and this pull up this voltage value. So, I am getting a 5 volt value, nearly 5 volt value at this point. So, this is the advantage of this wired AND connection. So, you see that pictorially you can see that the individual gates that I have, so they are actually open drain NAND gates. Okay. So, this is an open drain NAND gate and this is another open drain NAND gate. So, they are connected together and then when they are shorting, so we will be connecting via this we will be connecting via this this external resistor and pulling it up to high. So, that way it is this is going to F. Okay. So, this is the wired AND connection, and the advantage that you get is that, see, depending upon the load current that you need. So, you can control the value of this resistor. So, as a result you can make this you can make this resistance value low if you want a large current to drive the next state devices, devices, which is not possible with the normal gates, because there the current is fixed and it is fixed by the technology. So, if A and B are 1, output is pulled low. So, similarly, if C and D are 1, then also output is actively pulled low. If one gate is low and the other gate is high, then low wins. So, that is the wired AND feature that we are getting here. And then if both gates are 1, if both gates are 1, then the output will be floating, and in that case it is pulled to high. Okay. So, if in fact this should be, if both gates are low, this will be So, if both gates are low, so this output output of this, so if at this point, so if both A B are 0 in fact. So, whatever is there, so what we mean is that if you get the both of these two gates as open, then we can then this has to be pulled to high via this resistor. Okay. So, the two NAND gates, they function as the functions as ANDed, as if their functions are ANDed together. So, it is wired together to get the output. So, this is the wired AND connection. So, we will take an example and see how this NAND implementation can be done. So, we start with this sum of product form. Suppose that is the sum of product realization that I have. Then we add inverters between after for every line. So, we say at the output of the the beginning of the line and at the end of the line we have got inverters. So, these inverters are added, and then so this is equivalent to NAND, because this AND and invert. So, that is equal to NAND. So, this is my NAND operation, and similarly this inverter. So, if I take it here, so this becomes A bar or B bar or C bar. So, that is A B C whole bar. So, here also you get the NAND operation. So, that way we can getting the NAND operation, and NAND is nothing but AND plus NOT. So, then this AND part we can replace by wired AND. So, this AND we can forget, and then we can just join this together by means to make some wired AND connection. So, then this open collector or open drain gates, NAND gates can be used here to get the wired final circuit realization. Another method may be like this: instead of finding the circuit for F, the circuit for F dash is found in the first stage, and then there will be no inverter at the output. So, we can do it for F dash instead of F, and then we proceed like this, and in that case I do not need the inverter at the output. Similarly, we can have wired OR connection when open drain or collector gate with active low input. So, some logic family, so they will tell you. So, if you connect wires together, so you will get OR type of logic, and that OR type of logic, so that will give us the wired OR connection. So, that depends on the technology that we are using. So, if it supports, or if it says that if you connect two gate outputs, it will be acting as OR gate, then it will be an wired OR connection. Rest of the discussion remains same. So, you have to pull it low or pull it high. Okay. So, this that way we have to put some additional resistance and taking it to high or low. So, next we will be looking into another logic device, which is known as programmable logic array or PLA. So, PLA is like this, that is many a times what happens is that we need to realize multi output functional block. So, what I mean that if we have got some function, we have got a logic block where this A, B and C. So, these are the inputs. So, this A, B and C, they come as input, and this there are 4 outputs F0, F1, F2 and F3. There are 4 outputs F0, F1, F2 and F3. Now, this depends. So, this function, if we want to realize, suppose this is the so these are the functions. So, these functions we have got after drawing the truth table, after making the Carnot map, and so after doing the minimization. So, we have got it like this. Now, if you realize them separately, so you will need one gate for doing this operation, then one gate for doing this OR operation, like that. However, if you look into the terms, you see that there are many terms which are common between them. So, for example, say this F0, say this term B bar C bar. So, B bar C bar is used here as well as here. Similarly, your term AB is used in function F1 as well as in function F2. Okay, this term AB is used similarly in so many cases we have got reuse of terms. Okay. So, on the input side, so 1 equal to asserted term and 0 is negated term. So, and dash means it does not participate. So, that way, so this is just drawing the it is just noting down the terms like A B, B bar C, etc. So, if AB, the term AB can be represented as A and B, these are 1 and C is not there in the term. So, C is put as a dash. Similarly, B bar C, so A is not there, so A is put as a dash and B is put as a 0 and C is put as a 1. Okay. So, this way I am writing the input side for corresponding to the product terms that we have in this expansion, and then in the output side, if the corresponding product term is being used, then I will be putting a 1, otherwise I will be putting a 0. For example, the term AB is used by F1 and F2, it is not used by F0 and F3. So, this F0 and F3 I have got a 0 for the first row and I have got 1s for the F1 and F2. So, that way, so this is known as the personality matrix of the PLA, so of the programmable logic array. So, we will see what is a programmable logic array, but from this function itself we can make this matrix, the personality matrix, that is, you identify the product terms, you write down the product terms in terms of inputs and in terms of the variables, and then whether it is present or not, and if it is in the output side, you write down the functions and put zeros and 1s corresponding to the situation if the product term is not present in the function or present in the function. So, next we will see how this can be realized, like see, so we can see that as if I have got this A, B, C as the 3 inputs. So, we have drawn these inverted lines A bar, B bar and C bar, and these are all possible connections. So, as if I have got this AND gate has got connection from all the lines. So, second AND gate has got connection from all the lines. So, like that. Similarly, this OR gate I have got connection from all the 5 rows that are running. So, it is connected here. So, this is an unprogrammed device. Suppose this device is given to you where you have got this type of connections available, and I tell you that you choose the connections that you need to retain for getting the functionality. So, you can very easily choose the line connection that should be there to realize the function. So, all possible connections are available before programming, and after that we do some programming and then we take out some of the connections. So, unwanted connections are blown. So, there are some switches and those switches can be blown out by applying appropriate voltages to those points, and accordingly I can get a customization of this structure. So, we have got for the first term I need AB. So, rest of the connections are blown out for this AND term. Similarly, B bar C I blow out the rest of the connections, and A C bar, that is also our rest are blown out. So, this way finally, this A. So, this is only this AND gate is not necessary in fact. So, but this AND gate is physically present because that was part of the unprogrammed device. So, this A is coming directly here, and that is there is only one input. So, it is a one input AND gate, and then the OR gate we blow out the remaining connection and retain the minimum one. So, some array structures work by making connections rather than breaking them. So, this is also another type of PLA or programmable logic array that we have, where we make the connections rather than breaking the connections. So, both are available, both the families are available. So, this is another representation of this AND and OR, so this PLA. So, in this PLA you see that the first part of the circuit, so where I have got say this region. So, this region is representing the product of variables, and in this part I am realizing the OR of the product terms. The first in the left side whatever we have, that is the generating the product terms which are actually AND of these variables or its complements, and on the right side we have got the portion where it is doing the OR of the product terms. So, this part is known as AND plane of the PLA, this is called AND plane of the PLA, and this part, this right side, so this is known as OR plane of the PLA. So, the AND plane it realizes the product terms, and in the OR plane we realize the functions, the final output function in terms of the product terms. Now, these connections, so this in the unprogrammed device, so that is represented by the presence of all these crosses. So, it indicates that there is a connection, and there are fuses. Okay. So, each connection has got a fuse and you can blow it if you do not want the connection. For example, if you are trying to implement this function f0 and f1, f0 is a b plus a bar b bar and f1 is c d bar plus c bar d. Okay. So, then I have to do it like this. So, there is no sharing of term here. So, this a b, so these two crosses are retained. So, these two the rest of the fuses they are blown out. So, you get at the end this line on this line. So, you get the term a b. Similarly, on this line you have retained the connections a bar and b bar. So, they are ANDed here and you get the line a bar b bar. Similarly, you get here this c d bar and here you get c bar d. So, those connections are there, and now on the OR plane we retain these two connections and blow out these two. As a result, I get this a b or a bar b bar, and on the second OR gate I realize these two connections are retained, others are blown out. So, I get c d bar plus c bar d. So, this way this f0 and f1 are realized. Rest of the lines and rest of the product line, if there are more product lines available in the device, so they are not used. Similarly, if there are more number of output lines, so they are also not used. So, it's a more complex example. So, we have got a 3 variable function ABC and we have got 6 functions f1 to f6, multi output function with 6 outputs. Now, here also the AND plane consists of these ABC lines and they are inverted lines, and we are so we identify first the product terms. Now, you see this ABC this ABC and this A plus B plus C. So, they are all separate terms. Okay. So, this A bar, B bar, C bar. So, this A bar, B bar, C bar are coming here. So, they are ORed here to get F3, and for getting say say this A plus B plus C whole bar F4. So, how are you realizing F4? So, this is by means of this product line. So, this is A bar, B bar, C bar. Okay. So, this is by, so A bar, B bar, C bar are obtained, and that is coming to this OR gate to produce F4. So, this way we can realize any function. This F5, F6, so they are pretty complex. Okay. So, if you want to realize in terms of discrete gates, so that will require a large number of gates. But you see that once you have generated all the product lines, so you can just OR them together. For example, this A XOR B XOR C, the function F5. So, F5 you see, so it is consisting of all these terms A bar, B bar, C, A bar, B, C bar, A, B bar, C bar. Okay. So, these all the 3 odd lines odd terms are ORed together to get F5. So, that is the A XOR B XOR C function. So, this way we can very easily realize functions using PLAs, where the functions the terms are shared between the PLA, between the functions. So, for multi output function realization, this PLA gives us a very important strategy for getting them.